Hi and welcome to video 10 on this series of integration rules that are required for Specialist Mathematics Unit 4 Topic 1. And in this video we're going to talk about partial fractions, and it'll probably be broken down into a few videos. So let's have a look at the problems we're dealing with. So here's an example of a partial fraction. Now the integral of 5x plus 3 over x squared minus 1 dx looks a lot like something that we've dealt with before, where you've been asked maybe to separate the numerator and divide each component of the numerator by the denominator. But the difference is that the denominator in this case has two components, two terms, and that makes it really hard to integrate because you get down to here and yep, okay, maybe we could integrate that because 5x is a multiple of the derivative of x squared, but then this is quite hard to integrate, and maybe we could find a rule on the formula sheet to integrate that, but there's an easier way, and that is to do with partial fractions. Now partial fractions is not something that is going to be immediately obvious, but the procedure is quite simple as long as you learn it and you know the rules. So what if I told you instead that 5x plus 3 over x squared minus 1 is equivalent to, so the 3 equal sign means equivalent to or always equal to, irrespective of the x value, is equivalent to 4 over x plus 1 plus 1 over x minus 1. Now I'm going to teach you how to get from this side, the left hand side, to the right hand side and the working involved in that. A few things to note is you'll see that x squared minus 1 is actually a difference of two squares, and the factors of x squared minus 1 are x plus 1 and x minus 1. And that's going to be an important feature in this series of videos. Now, if we were to then integrate this, of course, we would get 4 log x plus 1 plus log x minus 1 plus c. And that would be a fairly easy question to do once we've broken that down into what we call partial fractions. So let's have a look at example 1, and through this example I'll show you how to apply partial fractions, and then we'll do a definite integral. So if you see a question like this and you see that there is a linear term or something and something more complex on the denominator, now in this denominator case you can see that if I derive that I get a linear term and I have a linear term on top. So the first thing I'm going to do is consider d dx of x squared plus 3x plus 2. What does that equal? That equals 2x plus 3. Now if this is a linear multiple of the top, well then we've got a really simple substitution question, and we let u equal that thing, and we'll find that the numerator cancels out when we work out our dx in terms of du, etc, etc. You've seen integration by substitution. But this has to be a linear multiple of the top. So I asked myself, how would I get from 2x to 5x? And that will be to multiply by 5 over 2. If I multiply 3 by 5 over 2, it will be equal to 7 over 2, which is not 2, and that's a problem for me. 3 by 5, so that would be equal to 15 over 2, my apologies. Still not 2, so this won't work. It won't work by substitution. We'll have a problem. So instead, I need to back right out and look at partial fractions. So here's how partial fractions work. 5x plus 2 over x squared plus 3x plus 2 is equal to, you're always looking for factors first of all. Now in this case I can tell you it's equal to x plus 2, x plus 1. In specialist maths we're not testing your skills with quadratics, so you're probably going to find it factorizes reasonably easily, or you're provided with the factors straight away. And of course, if you've got your calculator, you can go in and solve this to find -2 and -1, and therefore it's x minus -2 and x minus -1, and etc, etc. Now I'm going to say that this is equivalent to something over x plus 2 plus something over x plus 1. And so this equivalent to is also said as identical to. And there is some number here and some number there. It's always a constant over a linear term. Later on we'll see what happens when we have quadratic factors. But for now, a and b. Now all I'm going to do with this is I'm going to kind of ignore this part of it, and I'm looking at this only. and I'm going to multiply the whole thing by x plus 2 and multiply the whole thing by x plus 1. So I'm just basically getting rid of the fractions here. Now you'll see what happens is on this side they cancel out. I'm left with 5x plus 2 is equivalent to a x plus 1 plus b x plus 2. So in this term here, the x plus 2 cancels out, leaving just the x plus 1. This term here, the x plus 1 cancels out, leaving just x plus 2. That's why we get this. Now I can set up my expansion. Plus 2 is equivalent to ax plus bx plus a plus 2b. That's my expansion, and I've moved it into constant and linear terms. So I get a plus b x plus a plus 2b, and over here I get 5x plus 2. And what this means is that a plus b has to equal 5 and a plus 2b has to equal 2. That's the only way to make these equivalent statements work, and that's our identity rule. So you're going to set this out and build an understanding of how many x's you have on the right hand side and how big your constant term is in terms of a and b, and then write those equivalent statements that produce a set of simultaneous equations. Now I get this in the first one. I get a is equal to 5 minus b, and therefore I get 5 minus b plus 2b is equal to 2, which means that b is equal to negative 3, and therefore a is equal to 8. So I get 8 and negative 3, and so when I come up here, what I can do is I'll just shift this bit down because I'll need that, but not yet, to here. We can move it back up in a minute if needed. This is equal to the integral of, instead of 5x plus 2 over all that stuff, I'm going to write it as 8 over x plus 2 minus, because it's negative 3, over x plus 1 dx, and that's equal to 8 log x plus 2 minus 3 log x plus 1 plus c. Now move this back up. We do have a definite integral component to this. So now if I want to do this calculation for part B, I can just simply use my answer to part A and write this down as 8 log x plus 2 minus 3 log x minus, so x plus 1 between 5 and 3, and then do these substitutions. So I get 8, I might just zoom in on this bit, 8 log 5 plus 2, which is 7, minus 3 log 5 plus 1, which is 6, and then subtract from that 8 log 3 plus 2, which is 5, minus 3 log 3 plus 1, which is 4. And of course this does get out of hand because I have to bring the powers in before I can actually bring these together. So I could evaluate this now, but just to remind you of some log laws, that means it's log of 7 to the power of 8 minus log of 3 cubed minus log of 5 to the power of 8 plus log of 4 to the power of 3. And what have we done here? Minus 5 plus 1 is 6, isn't it? So that should be a 6. And that becomes log 7 to the power of 8 times 4 to the power of 3 over 6 to the power of 3 times 5 to the power of 8. And you can evaluate that. It's going to be something possibly big. I'll leave that with you to deal with. So there we have our integration using partial fractions. And there's an example. And this process here is going to be really important.